Welcome back to the Hyperthesis podcast episode 80. We got 80 this time. My name is Pheely.
I'm Patrick.
And I'm Liam.
All right. So today we're going to be talking mainly about one topic that Patrick got from his conference, which is on spectroscopy and, the different things about that. But before we get started, anyone have any intro topic?
I do. Not so much related to spectroscopy or anything Patrick's probably going to talk about, but who knows? So as usual, I found a paper, and it was titled "Water Striders are impervious to raindrop collision forces and submerged by collapsing craters," which is kind of a weird title. But basically, it was this paper published in PubMed in January this year by some researchers from the United States and Turkey. And this paper studied how water striders, which are these tiny little insects that can walk on top of water, and they're often found in humid, rainy areas. The paper studied how they were affected by rain, basically, because if you're very small and raindrops are very big, and your survival depends on floating on water, you might get sunk by the raindrops, essentially. So they put these water striders in a tank, and they used some high-speed videography and imaging analysis, and they just looked at how the water and the bugs, or how the bugs handled being hit by raindrops, how it had an effect on them. So these a typical water strider, they have these strong exoskeletons since they're bugs. We think of like an ant or a beetle or something. So it allows them to survive being hit by a raindrop no problem. And because these insects are both hydrophobic, so that they repel water, combined with the fact that they're quite light and don't weigh very much, sometimes when they're hit with a raindrop, they'll kind of they'll sink in the water a bit, but they'll float right back to the top, or they'll bounce right back out. Like, when you're in a pool and you have a ball full of air and you submerge it below the water, and then you let go and it shoots up out of the water due to buoyancy. But sometimes the raindrops, if they hit the bug hard enough, I guess, the bug can sink into the water and get submerged, and then they have to swim back to the top or they'll drown. So the paper states, the paper states that these water striders, the raindrops can weigh up to 40 times their mass. So depending on how big or fast the raindrop is, it might not really bother them, or it might cause them to become submerged, and then they'll have to swim back to the surface. And I'll get to why this paper is even studying this soon. I'll circle around.
Well, I think, raindrops can be quite large, right? I don't know if you guys been like heavy rain where like the raindrop actually hurts your skin. It's like, ooh, that's kind of that hits. But I wonder what happened to like, those small animals and get hit by like the raindrop, the size bigger, where their sizes are smaller than the raindrops, right? So like getting like blasted with a huge cannon basically from the sky. I wonder how they survive that. Or be under a tree would help.
There's a scene in the B movie that answers that question. They'll overthrow your government, or whatever happens in the B movie. Maybe not quite that, but
I've never seen the Bees movie. What is it called? Is it called The Bees?
Called the B movie.
Like the B movie?
Yeah, the B movie. It's a classic.
Is it like an animation?
Yeah, it's like a Pixar movie, I think. Maybe it's not a Pixar. I don't know, but
I think I've seen the character before. Like a yellow and black bee thing with like a human-ish face, right?
Yeah, the movie's pretty cursed, honestly, but it's hilarious. Anyway, yeah, there's a scene where the bee he can't fly because the rain's hitting him, and he has to land on a windowsill and hide from the rain. So Anyway, we're not talking about bees here. We're talking about these water striders. They're these, the bugs. They use surface tension to walk on top of water, basically. So if a raindrop hits them and breaks that surface tension, there's a good chance they could sink into the water. And they're not they breathe air, so they'll drown if they sink into the water and don't resurface. So anyway, where does physics come in? Well, it's I don't know if it's really a physics paper, but it involves surface tension, right? And they kind of take a physics approach to solving it. They break it down into some simpler parts. So they basically kind of break down the mechanism of a raindrop hitting one of these water bugs. And it can be broken down into either two or four main steps. So the first two steps are they kind of always happen, and then the second two steps, the third and fourth ones, they'll happen if the raindrop's big enough and moving fast enough. So the first two main steps, the raindrop comes down and hits the bug, and it forms. What it does is it kind of pushes the water down, and it forms this little crater underneath the surface of the water, and the bug kind of sinks down into it. And the second step is that the crater will kind of collapse back up to the surface and it'll shoot the bug out of the water like a little spout. Like, if you've seen these like war movies where a torpedo goes off underwater, the water like sinks down, then shoots back up in this big spout. So the raindrop hits the water, it sinks down, the bug goes down with it, and then it shoots up in the air, and the bug gets kind of like shot into the air a little bit. Um, However, if the water droplet's hitting the bug really fast, or if it's a really heavy raindrop, what happens is that after the spout shoots up, there's a third step, and a smaller second crater forms after the water comes back down, and the bug sinks into that smaller crater, the third step. And then the fourth step is that the little tiny crater kind of goes back to the surface. And it actually turns out that this smaller second crater going back to the surface does so really fast. This paper found that this smaller second crater moves back to the top to the surface about 50 times with the 50 times the acceleration of gravity. So it shoots back up. It accelerates quite fast. I mean, it's for a very short amount of time, but the acceleration's so fast that the water bug's surface tension can no longer keep them floating, and then they'll sink through as it kind of goes back to equilibrium, and so that's how they sink into the water. So they have to be fast raindrops and heavy raindrops, but there's this four-part mechanism, and it's the final part. The water accelerates back up really fast, and the bugs can sink through. So there's the main motivation for this was not water bugs. It was actually understanding the dynamics of microplastics in water supplies. So for people who might not know, microplastics are these tiny little bits of plastic that come off of, wrappers or bottles or anything that's made of plastic, and they found their way into virtually all water on the planet, I think. I'm not a water expert, but at the deepest depths of the Mariana Trench, you can find like plastic water bottles and stuff. So I imagine microplastics are just everywhere.
Well, the thing is, not all plastics float, right? So the pollution in the ocean that we see are only the floating plastics, but a lot more. I think some people project it to be like the real, like it's like the deep iceberg, right? Like 90% of the plastic waste in the ocean are actually the one underwater that we don't. It's really hard to measure that.
And just to demonstrate how everywhere it is, on average, some estimates say that humans eat and drink about 5 grams of microplastics in a week, or about the weight of a credit card. So just imagine eating a credit card every week, and that's what we're ingesting in terms of microplastics.
Jeez, kind of scary to think about. But we eat all of our food that comes from plastic wrappers, and a lot of people drink out of plastic water bottles. So it adds up, I guess. But there's a lot of similarities between microplastic and water bugs. It turns out because they're both very light. They both tend to float due to surface tension. So the researchers are kind of approaching this from um, the way they think of it is that like a water bug is a good model of a piece of microplastic. I don't know if that was the original purpose, but that was kind of like the conclusion of the paper. because a lot of microplastic will float due to surface tension, but the rain will actually cause it. This big and heavy enough raindrops will this four-step mechanism they propose for the water bugs will actually apply to the microplastics, and it'll cause them to go under the water. And once they're under the surface, they're much harder to remove, and they can cause a lot more problems for an environment. And microplastics, they have a lot of health risks. It turns out, to name a few, they can cause respiratory and digestive problems, increased risk of diabetes, and they can actually disrupt your sleep schedule. People have found out, assuming you're eating a lot more microplastics than I guess the average. So basically, one of the long-term goals of this study is to move their research from water bugs to microplastics. So they kind of come up, they started with water bugs, and now they want to look at microplastic a bit more and understand the dynamics. How does this raindrop, does the exact same thing happen with the microplastic that happened to the water bugs? Is that actually what causes a lot of surface plastics to go underwater?
It's very interesting that they started with water bugs and will move on to microplastics, just because you think it'd be easier to do the reverse, where you're working with an inorganic material that's actually quite easy to record its position. There are essentially types of microplastics that have a reflective coating, so you can shine a laser and see where they are. This is done for a lot of like different flow experiments, or like circulation experiments in water, where they just put a whole bunch of like essentially glitter in the water and then use a laser or a very bright light to track where they all go. So saying that they'll move on to microplastics from something like water striders, just, I don't know, that seems counterintuitive to me if you aren't interested in the water strider bugs.
Yeah, so I mean, I might be wrong when I said that. I didn't fully read the paper in all of its glory. So maybe they started with microplastics and went to water strider. The kind of, from what I could tell, the paper was about water striders, and then they kind of comment on microplastics throughout it. So my guess is that they probably weren't originally interested in microplastic, and then kind of halfway through maybe realized that, oh, this is like a big application of that. But again, I could be wrong. So citation. Well, we have the citation, but we need to read the citation more, or I do maybe. Um, yeah, so they're planning to study microplastic in the future, and they also want to study other things regarding the water striders themselves as well, because it turns out that a lot of the time what they would find is that a water strider got submerged, and then it would swim back to the surface. And each successive time it became submerged, it would take longer to get back to the surface, or it would become less buoyant because there's this small layer of air. Because the water striders are hydrophobic, which basically means they repel water. If you've learned high school biology, you might have learned about that a little bit. But each time they get submerged, their hydrophobic little bubble gets smaller and smaller for certain reasons. It might be contaminants in the water. It might be they have little hairs on them that get wet or something. I don't know. So they want to study kind of how that works. And then another thing, which we've talked about before, biomimicry, which we had a whole episode about at some point. There's applications of applying the science they learned to design little water strider robots, or applying what they've learned to kind of submersible robots. I couldn't tell you what the exact applications are, but there might be some.
I mean, that's certainly very cool to I look at something that we know about, like surface tension, and see, because it's a completely different world for not only hydrophobic materials, but also just for small things. So you hear things like, oh yeah, microorganisms that swim in a pond, it's like they're swimming through a jelly instead of like us swimming through water in a pool, for example. So it's really interesting to look at the different effects that scale has when you're interacting with something as common as water. And then also just in terms of buoyancy, there's a lot of effort going into cleaning up the ocean's plastic. So like we have the Great Pacific Garbage Patch, and there are some really neat initiatives that are trying to remove as much of that garbage as possible. But of course, these microplastics are being missed, or they're too deep. And so maybe this will help like understand exactly how deep they can go. so we can see how they're sinking and how they're actually getting under the water, and then maybe able to measure, okay, where exactly are they going from here? So we can target certain layers, say within the Pacific Ocean, to extract more microplastic.
Yeah, because if they're right, and it turns out that rain is a major source of submersing microplastics, then you could maybe, make a map of the world and say, all right, these areas it rains a lot, so there's probably more microplastic, or, I guess it depends how much plastic there is in different parts of the world, but assume everywhere in the world has the same density of plastics starting off on land. Bad assumption, but,
Very
yes, a
physicist
very
approach.
physicist approach. It's a 0th order approximation. But then you could say, okay, areas with more rain are going to inject more microplastic into the ocean than areas with less rain, and you can build models from that maybe, or things like that. That's something you could probably understand a bit better through their research.
All right. Thank you, Liam, for the intro topic. Well, now we gotta move on into our main topic, which is on some
Pastrami,
spectroscopy techniques.
the pastrami technique.
Yeah, the pastrami techniques. So first, you want to slice your meat really thin. No. So as you may have noticed, I was not here for a previous episode, and I will not link that in the description. But I was actually away at a conference that focused on imaging spectroscopy.
Me and Pheely had to manage without you. Without you to keep us on track, we basically just talked about random crap for 60 minutes.
And I hope the audience enjoyed that.
Maybe.
But yeah, so I was in Valencia, Spain for an imaging spectroscopy workshop/conference. So there were a lot of presentations, but it was more so advertised as a workshop because it was essentially a way for all of us to come together and talk about different experiences with common sensors that we're using, whether they be handheld ones or orbital-based ones. But the general idea was to talk about new research that's being used to both analyze and utilize spectroscopy, whether it's for vegetation or geology or resource management or a whole bunch of other things. There was even one cool talk where they were able to point one of these spectroscopic satellites towards the Earth at night to see how things light up, which was super cool. But just to give a little bit of background of spectroscopy, just because it's more so an experimental thing or a data side thing, less so you see it in theoretical physics. So at a very base level, light or electromagnetic radiation interacts with matter depending on the wavelength. So different wavelengths will interact with matter differently. And we've definitely touched on this in previous episodes, especially even with some guests. But this is a very important fact that light interacts with matter differently at different wavelengths. So generally shorter wavelengths of electromagnetic radiation, also known as higher frequencies, same thing, interact with smaller things. So visible light, for example, tends to interact on the molecular or atomic level. So we see, for example, emission lines from hydrogen, or a lot of the different emissions from elements can be categorized into certain visible wavelengths.
Yeah, I mean, the way I always think about it is just things interact when they're around the same size, right? I don't know if this is a good analogy for small things, but not so much for big things. But, if someone throws a grain of sand and it hits me in the head, I'm probably not going to notice it. But if they ream me in the side of the head with a dodgeball, I'm going to feel it. That I don't think that holds true for bigger things, though. If I get hit with a wrecking ball, I'm still going to feel that. But
Well, I think it's about momentum. You get hit by a bullet. It is small. You gotta feel it maybe for a split second before you die.
yeah, it's an analogy. It's not perfect.
But at least in terms of electromagnetic radiation, that does hold true. So things interact about on the same size. So hundreds of nanometers of wavelength for light will interact with something that's on the order of hundreds of nanometers, like atoms or molecules. UV light will also interact with atoms. If we move really far down, like X-rays, those will tend to interact with the electrons or the nuclei within atoms. And then cosmic rays will just rip everything apart. The cosmic rays are kind of like your wrecking ball analogy, where it just destroys everything.
Yeah, I think, well, the interactions happen when we consider those waves as waves, right? And that interaction range basically is a wave phenomena that happens. But for some things like the photoelectric effect, for example, when you get certain, enough momentum, enough energy, then it's become a little different.
Yeah, and of course there's comptons and scattering too.
There's still a wavelength interpretation of that. I forget the exact details, but it's like the kind of electrons. I don't quite know how it works, but there's basically like a Compton, the Compton wavelength of a metal, I guess, right?
Yeah,
I forget exactly where it comes from. It's this periodic lattice crystal calculation, probably.
Yeah. But again, generally, visible light will interact and, for example, produce a photoelectric effect where enough energy is provided that the electrons just flung away from the atom. And then if we go the other way, we see that, for example, you can't interact with atoms using microwaves or radio waves, but for things that are on the same order, like, for example, buildings, we can use radio waves to figure out where buildings or where structures are. But for spectroscopy, it mainly focuses on the UV, visible, and infrared regions of light. So, and especially for remote sensing spectroscopy, they do not focus on UV really at all. There's some niche cases, but ultraviolet light does not pass through the atmosphere that easily, so it's not really looked at. So a lot of the talks that were given focused on visible and infrared wavelengths of light. And these tend to interact with both the electronic components of materials, along with kind of the actual physical modes of different molecules, like their vibrational modes or rotational modes.
Well, about the UV, if a few years ago we didn't ban globally, like the CFC, the ozone hole's gonna be like so huge that we will get the actual UV, and maybe the scientists had some more wavelength to play about at the cost of some cancer. But now the ozone layer is healing really well, so it's good.
Although that being said, there was a very good Veritasium video done a few years ago where he was able to take the UV filter off of a camera, or he used like a special UV camera, and when he points it towards a clear sky, it's still hazy, just because UV light has trouble passing through the air itself. And of course, we have the ozone layer to thank that we aren't bombarded by UV radiation that does make it through. That being said, though, it's still not the best when going through the atmosphere. But so this whole process of measuring these different wavelengths, or kind of looking at both the chemical and then physical composition using visible and infrared light respectively, involves the absorption and emission of light from these atoms. So for spectroscopy, you tend to have this light source, whether it be a very controlled light source like a white LED, or the sun, which is what's used for orbital remote sensing, or just a lot of different spectral remote sensing. And so you have this white light, ideally, that's bouncing off or directed towards an object, which is then reflected at certain wavelengths, while other wavelengths are absorbed. So again, that absorption can take place at the electronic level or at the molecular kind of vibration rotational level. And depending on what's absorbed and what's reflected, you can tell what the chemical or elemental makeup of something is. So again, at a very basic level, if we were to just provide some energy to hydrogen atoms in a gas, then we see very distinct emission lines. from that gas coming from the electronic processes. In the case of hydrogen gas, it's might be H2, or it might just be pure hydrogen. But in that case, we see very distinct lines. Now, as you increase the number of electrons or increase the molecular complexity of something, then you get a lot more different emissions. And then you can also look at the structure of different things. So there are certain bands within, or certain wavelengths within infrared light that look at the structure of, or microscopic structures that cause the light to be constructive and destructive with itself, which can also be measured as a kind of absorbance or emission or reflection. So there's a lot of interesting things that we can actually do with this information. And one of the primary things is actually determining the chemical composition of things. So this is something that's commonly used in chemistry, commonly used in biology as well, and also a lot in remote sensing. So if we have, using an example I'm familiar with, something like a leaf. So leaves appear green to us. They are very green. You can see changes in leaves over time, especially right now. It's supposed to be spring. So we see things greening up, and then throughout the summer, they get a nice dark green. They're absorbing a lot of the solar radiation that comes. And then during the fall in Canada, any deciduous tree, the leaves start to turn brown and die, falling off the tree. So if we were to look at a very nice green leaf and look at it in the visible range, we see that it absorbs like pretty much every wavelength except around kind of the yellow and green wavelengths. And that's why they appear green, because they're reflecting green light and absorbing everything else. If we look beyond the visible in the infrared, we see a massive spike in its reflectance so that it's very, very reflective of certain wavelengths of infrared light. But leaves also have water. So at, again, other wavelengths of infrared light, you'll see very massive absorption by the water that's contained within it. And then we can also see some of those structural features, like with what's known as the spongy mesophyll, that also has some absorption features. So there's a lot going on, but based on the spectrum of light that's produced in the visible and infrared regions, we can figure out properties about the leaf, including chlorophyll content or carotenoid content or water content even. We can figure out how healthy trees are just by looking at how much they reflect infrared light versus red light.
I think this raises a more what's called fundamental question, at least for me, is like very non-scientific question. Because like when you say something is green, right? If I don't know physics, be like, because green is a property of it, like or like an object is green because there's something it's green. But what reality is that it doesn't want green, so it's just rejecting green back to us. So we see it as green, it absorbs the rest of the colors. So in its essence, it has the rest of the color except green, right? So it's like the inverse.
So a really cool thing is, for example, in your camera, in your smartphone, say, or in your laptop lens or whatever camera you're using, it's made out of red, green, and blue pixels. For the green pixel, you'd think, oh yeah, they just put a green filter over it, so that's able to just record green light. But if you were to put a green filter over it, it's taking in everything and then reflecting green light. So it's actually not detecting green light at all. To solve that, you have to make it pink, because pink is white light minus green wavelengths.
Well, there is this too, right? But back in the days, people used negatives. So it's literally the opposite of that, right? And did we do a story about, we did a story about photography and films, right? I remember that, different type of grains that record different colors. But I think spectroscopy use kind of the fundamental nature of that in a more extreme sense, where well, it's not just three colors; it's wavelengths which are continuous, and each element or each molecules would have a distinct or unique, sometimes maybe not too unique, but usually they're pretty distinct profiles that just say, let's say, if you look at the Fourier transform, for example, you're gonna have different peaks at different places, and different materials gonna have different peaks at different places. And astronomers use this kind of method to devise what's in the stars or planets, right? What materials exist. That's why we know that oh, maybe iron exists in this on this planet, but we never been there. We don't even know what it looks like in terms of like as the same resolution as Earth.
So you hit on a very good point there, and it's the resolution. So you said that a spectrum is continuous, but realistically, that's not something that's really achievable. We need to have some sort of spectral resolution, and that's something that's very important. Is when you're trying to record the spectrum of something, like reflectance or the spectrum of a star, you're going to have some sort of resolutional limit between the wavelengths of light that you can distinguish. So, for example, in one of the sensors I look at, it has about 235 bands, or different wavelengths that it can measure between 400 and 1,100 nanometers. So there's a spectral resolution in there. So it's as continuous as we can get, but still not perfect.
Well, but those are instrumental limits, right? They're not. The lights that come in are continuous, and maybe. Well, one could say that there are Planck scales that make it a little more discrete. But hey, well, but that's this very small scale. But for example, like in sounds where we are recording, there's a bit rate and there's the frequency of the data. Was the same thing, right? When back in the days we had CDs, which I think are 320 kilobit per second or something like that, right? Maximum. And the quality was okay. And then when we have lossless, and become great, like comparable to vinyl, where basically it's like an analog recording. So basically, you get they made the groove to follow this kind of continuous path of the amplitude or recording the frequency of the sound wave, but in a sense that also limited by the width of the molecules of that, because you're building blocks of what do you call it, contours of the amplitude of the sound, but those building blocks are limited by the size of each component that builds that groove, right? And those are molecules which are very small. So, and I think it also depends on your little needle head that used to probe that too. So there are multiple what's called factors that are contributing to the sound quality. I think it works really similar to spectroscopy, where well, even though how much can you record and at what resolution can you record, right? And maybe there's something hidden that maybe only be seen in high resolution. Maybe we will know exactly the distribution of each peak. Maybe we know a lot of it too. Maybe it's Lorentzian or something, right? Because they are with the response function that come out of electronic transition, like, and those theoretically we know what they should be.
Yeah, I mean, in spectroscopy, it's good that you brought that up because there's kind of two main different sensors that you can use. One is a multispectral sensor and one is a hyperspectral sensor. They're trying to move away from that language, but for demonstrational purposes, it's easy to say. But for multispectral sensors, they tend to have a much wider kind of set of wavelengths that they can detect for each, I guess, range of wavelengths. So in a multispectral sensor, you might have 11 different regions that it's able to detect. So it's low spectral resolution. But of course, it's a lot easier to do. Whereas when we had these hyperspectral you have a lot smaller spectral resolution, so you're able to see a lot more detail. But of course, that lends itself to problems as well. And the other thing is that with any kind of spectroscopy that you're doing, um, it is continuous, but you're assuming that the wavelengths being recorded are the peak wavelength. So for each individual wavelength that you can record, there's a distribution of wavelengths that will record. So you have this peak, and then it's kind of like this normal curve where it spreads out on either side. So you might be able to record, say, 400 nanometers plus or minus half a nanometer on either side. So there's also some uncertainty in what you're recording.
Well, I try to recall there was this like half width, half something, right? That people look at.
Yeah.
What?
Full width, half max, or half width. Yeah.
Yeah, something like
Something
that.
like that. Yeah. And so that's exactly it, is how we can determine the uncertainty of what we're recording is the full width, but half the maximum height of that kind of normal distribution. And of course, the distribution isn't always normal. It depends on the sensor, but we can kind of approximate it as something that's normal. But yeah, there's a lot of really cool things that we can do with this. So you mentioned one thing, which is looking and trying to figure out what things are made of in space. So whether that's stars and trying to figure out what elements are they're composed of, or like a friend of ours looked at, Heather from our undergraduate degree. She was looking at diffuse interstellar bands and trying to figure out just what kind of complex carbon molecules were contained with them. And these like range from 20 carbon long molecules to like 60 carbon long molecules. But that was all using spectroscopy from stars, the light of stars that was passing through these bands of diffuse gas in the interstellar space before we were able to observe them here on Earth.
Yeah, there's so many applications of spectroscopy, right? There's one I always remember as one of the Mars rovers, or maybe it was multiple of them. I don't know how many Mars. I don't know anything about Mars exploration. I'll be the first to admit that. But at some point, there was a Mars rover that basically what it did is it would fire this laser into the dirt. It would take like a sample from the Martian surface of the dirt. It would fire a laser at it. It would kind of create. It would ionize it. It would create a gas, and then it would look at the. It would do its spectroscopy. It would look at the lines emitted from the light and the gas, and it could tell like what was the surface made out of. So that's kind of a niche application, but there's all kinds of them.
I mean, I would say that's not so niche. So spectroscopy is used a lot in geology to figure out what you're looking at. So there's a really cool and massive machine in the lab that's next to mine where essentially you can put a rock core. So you take however deep a core of rock of wherever you're interested in, and then you can run it through this machine. And as it's like going under the sensor, it's scanning. And so you can get a spectral signature for whatever is being run under there. So you can do something similar, not quite as intense, burning things up with lasers in the Mars rover, but you can still look at the spectral signatures of different rocks as they pass under the sensor.
So at your conference, were there any niche applications of spectroscopy, or what did you do? What did you present, and what did you hear, and what did people talk about at your conference? How did it go?
Okay. First of all, the conference was excellent. If you ever have the opportunity to attend a conference in Spain, especially in the south of Spain, go. The food is incredible. We were served paella and wine every day for lunch. So really good.
My Italy conference experience was very similar. It was just such good food and wine, and just every day for every meal too. It was North America's kind of sad now that I think about it.
Yeah, every conference I go to, I've been to in North America, is like, go fend for yourself for lunch, buddy. Or you can have this sandwich and a juice box. Like, wow, am I 12?
Yeah, I know. The conferences in Europe or maybe other parts of the world too, I'm sure. But like Europe and Asia and everything I've heard from other people at conferences in different parts of the world, that you get treated properly, like you're saying in Spain, and when I was in Italy, it was, full catered meals every meal.
But yeah, so aside from the food, the conference was also very good. There were about 270 people. Quite a few of them were German. In fact, I think they made up the plurality of people, followed by Spanish, and then, of course, lots of other European countries. There were exactly 4 Canadians there. Um, but so a lot of the talks did focus on spectral remote sensing, especially with the large German presence there. Their German space agency is responsible for 2 out of the 3 major hyperspectral sensors that are used in orbit. So there was a lot of talk with those, especially this was the first conference after the launch of NMAP, which is the German space agency's newest standalone hyperspectral satellite. So a lot of cool things to do with calibration, and proper corrections. So, for example, for these hyperspectral satellites, they have to look through the atmosphere and figure out where they're looking on the surface of the Earth. So, when you get your raw product, it's just essentially digital values of, okay, there it's this brightness at this wavelength kind of thing. And so they can take that and they can say, okay, we're going to just show that image in our like lowest form, which is known as level 1, where they don't do any correction to it. Then what they can do is they can do geometric corrections with it. So depending on the sensor geometry and defects within the sensor itself, they have to apply different effects, like smile, it's called, where there's a different response. So I guess different intensities as you move along the width of what the sensor's scanning. And then also what's known as keystoning, where you have to look at the distortions caused by the sensor itself. So kind of like if you have a fisheye camera or a fisheye lens on your camera, it's quite distorted. So you kind of have to correct for that type of thing. And then a really challenging thing that was discussed quite a bit was atmospheric correction, because this light has to pass through the atmosphere not once, but twice. So you have to do a lot of first calibration with the sun. So seeing exactly how the sun reflects off a perfectly like reflective surface, but not like a mirror. That's specular reflectance. It's diffusely reflective. So you have to calibrate based on the sun and then put a shutter over everything so no light can get in, and get your dark current to understand what your noise is like. And then once you have all that, you can take your spectral data, and then you have to do an atmospheric correction, which you have to understand what the atmosphere is like over the area that you're looking at. So things like water content, there are giant absorption bands in the infrared for water content. And then there's also other things that you have to consider. So there was a lot of talk of proper calibration and corrections for these data.
I feel like those data are going to be super useful in like weather prediction, right? Because a lot of times it's not accurate when we don't know exactly what's in the air. Because like, well, if you don't know exactly what's the water content of the air, well, how do you predict rain?
So these satellites aren't the best for weather prediction, just because, I mean, there's only like 3 of them, and they can only be active for so long for each pass of the light side of the Earth. So we actually have a lot of other satellites that are able to do that, but they are good for long-term monitoring. So an excellent use case of it was detecting methane leaks from different plants and areas. I wouldn't say where, just in case I make a mistake, but essentially they were able to detect massive methane leaks using these sensors, and over time as well. So they were able to repeatedly go over the same area every so often, and kind of on the order of weeks to months, and saw that there was still leak, and then measured the severity of that leak. So it's useful for longer term things, and also the weather to some extent, so we can understand longer term processes like, say, El Nino or the whole Enzo cycle. But yeah, it is still incredibly useful data. And the fact that we're collecting so much of it is very useful, especially in the future when we want to look back.
All right. Well, thank you, Patrick, for bringing up the spectroscopy stuff from your conference and these technologies, the advancement that's going on. Well, to kind of before we get to the story, we will get Patrick to tell us how to reach us and how to, follow us.
Well, congratulations for finding us, and thank you for joining us on our 80th episode. Crazy that we've gotten this far, but that just means we have a very large back catalog which you can listen to. We are based out of Spotify, but you can find us on whatever podcasting service that you use, whether it be Google Podcast, which is soon to be killed in Canada, RIP, or Apple Podcast. There's also Audible. We're on pretty much whatever podcasting service you may use. Now, if you want to find our kind of non-podcasting content or get updated when we are posting content, you can check us out on Instagram. We are at the Hyperthesis. So you can see updates, you can see fun pictures. We had a meetup last month, which was a lot of fun in Toronto. And I don't know if a picture was posted for that. I haven't checked the Instagram. I'm getting a nod yes. So you can go check that out and see the Hyperthesis team reunited since like February 2020. So that's a great place to see all of our updates. You can also send us a DM if you would like to reach out to us with questions, comments, or if you are an expert in your field. We have had a lot of guests on the show, and we are always looking for more and curious about what you do in your area of science research or expertise. The final way to reach us is through Gmail. We are hyperthesispodcast@gmail.com. You can send us an email on there, and you can also find us on YouTube. You can just search in Hyperthesis Podcast in the YouTube search bar, and you should be able to find us. So feel free to like, subscribe, comment, do whatever you need to do, and share us most of all, and let us know if there are any topics you would like to hear on this show.
All right. So for today, we're going to do something that is a little different. Well, when I think of spectrum, I think the word has been used more colloquially these days, right? And, there's a lot of usage for the word spectrum. So I want to get into the roots or the meaning or the structure of the word spectrum itself first. And I like to study the origins of words or the field actually called etymology. And the word spectrum is started in 1610s around there. It means apparition, phantom, or spectre when you hear the word spectre, right? It is now it's kind of obsolete. It's from the Latin spectrum, or in plural is spectra. And so it means an appearance, image. And it's from the word spexere, which means to look at or to view. So the visible band showing the successive colors formed from a beam of light passed through a prism. So this definition was first recorded in 1670s, and we have been using it to explain like wavelength and such of visible light pretty commonly by 1888. And this new sense of like this figurative sense of meaning that like, oh, it's a range of thing or anything at all has a range, it's a spectrum, started in 1936. So it's been not too long actually that we have this meaning of spectrum. And I'm going to pivot into something different. I found out that my favorite poet actually wrote a poem, had the word spectre in it. So I'm going to take that poem and read it. Why not, right? And it actually doesn't really have a title per se. He wrote a lot of like songs and ballads and little short poems. So, but I think people call it My Spectre Around Me, Night and Day by William Blake. My spectre around me, night and day, like a wild beast guards my way. My emanation far within weeps incessantly for my sin. A fathomless and boundless deep, there we wander, there we weep. On the hungry, craving wind, my spectre follows thee behind. He scents thy footsteps in the snow, wheresoever thou dost go, through the wintry hail and rain, when wilt thou return again. Dost thou not, in pride nor scorn, fill with tempests all my morn, and with jealousies and fears, fill my pleasant nights with tears? 7 of my sweet loves thy knife has bereaved of their life. Their marble tombs I built with tears, and with cold and shuddering fears. 7 more loves weave night and day round the tombs where my love lay, and 7 more love attend each night around my couch with torches bright, and 7 more loves in my bed crown with wine my mournful head, pitying and forgiving all thy transgressions, great and small. When wilt thou return and view my loves, and them to life renew? When wilt thou return and live? When wilt thou pity as I forgive? Never, never I return, still for victory I burn. Living thee alone I'll have, and when dead I'll be thy grave. Through the heaven and earth and hell thou shalt never, never quell. I will fly and thou pursue, night and morn the flight renew, till I turn from female love and root of the infernal grove. I shall never worthy be to step into eternity, and to end thy cruel mocks, annihilate thee on the rocks, and another form create, to be subservient to my fate. Let us agree to give up love, and root of the infernal grove. Then shall we return and see the worlds of happiness eternity. And throughout all eternity, I forgive you, you forgive me. As our dear Redeemer said, this is wine and this is the bread. Oh, that's my recite maybe some, I don't know how to really read poems, so it just goes by my spacing, I guess. It is what it is, boys. Well, thank you for listening. I hope you get something from it. Blake is really good at duality of things. Well, thank you for listening and take care.
Bye, everyone.
See ya.